So, welcome back to this NPTEL lectures on and this lecture as well as the next lecture I will be discussing that wear of friction and wear of ultra high temperature ceramics little and or high temperature ceramics mostly on the titanium diboride, and another one is that niobium boride. Although we are not discussing this in more details, which I will be doing in the next slide, is this titanium these transition metal borides. Like zirconium boride, niobium boride, and to some extent titanium boride. So, these are these are transition metal borides. They belong to a generic class of materials which we call as UHTC. UHTC stands for ultra high temperature ceramics. Since this is not a course on ceramics, but this is a course on tribology, but as I mentioned to you multiple times that this course is unique because here our focus is to understand the wear mechanisms of a broad range of ceramics as well as metals, and these understanding of our wear mechanism would be useful to develop next generation materials for better and better wear resistance properties. Now, these particular ceramics so like titanium diboride and zirconium diboride, these kind of materials that consolidation or densification of these materials is fairly important and which is not a very easy task. So, some of the things that which are important, it is sinter 8, like what is the addition of the sinter 8 and sintering temperature or sintering conditions, sintering temperature, sintering time, etc. So, these are the parameters which needs to be optimized while consolidating these materials. Now, people in the past has used some of the metallic sintering aid like nickel or copper or iron to consolidate titanium diboride. Now, what happens when you add these metallic materials? These metals, depending on the sintering temperature, these metals can melt and giving rise to liquid phase sintering, but because of the liquid phase sintering, your grain morphology also would change, like microstructure would change. But the point that is more important, that if we use these materials at high temperature, then what happens at high temperature, this metallic phase again will be molten, and therefore, you cannot use these materials at high temperature. So, the use of metals will severely restrict the application temperature of these classes of ceramic. Now, keeping this in mind, what we have used and what you will see in next 25 minutes or so, we have used that different type of sinter aid. One is molybdenite, because molybdenite also is one of the materials for high temperature applications, because some of the high temperature furnaces you will have this molybdenite as a heating element. And while analyzing that microstructure and phase composition of TiB2-MoSi2 composites, what we have noticed that because of the sintering reactions, TiB2 react with molybdenite to form TiSi2 or Ti5Si3. So, the next level, at the next level, what we have done, we are trying to understand whether we can use the TiSi2 directly to TiB2 in order to develop another classes of materials like TiB2-TiSi2 ceramic. So, these are the two classes of ceramic materials mostly based on TiB2, but with different sinter aid. One is molybdenite, one is titanium disilicide, and we have used that hot pressing as a technique to consolidate these materials. So, depending on what is the sinter aid type, we have used the sintering temperature and we have tailored the sintering temperature, but hot pressing is the major consolidation route that we have utilized to densify these particular ceramic materials to more than 99% theoretical density. So, 99% Roorkee, that is the theoretical density of these sintered materials. So, what is this property requirement for high temperature applications? One should have, this material should have high melting point, there should be strength retention at high temperature, high creep strength, good thermal conductivity, microstructural stability, and good oxidation resistance. Now, this is the titanium boride binary phase diagram. So, those who are not from metallurgy background, essentially the phase diagram is the two-dimensional space which describes the stability of different phases in temperature composition space. So, that is how typically undergraduate students in metallurgy learns in the university, that essentially a phase diagram to any metallurgist essentially means temperature versus compositional variation. Here if you see along the x axis, it is atom percent boron which is varied from 0 to 100%. Now, how to find out that which are the phases that are present? For example, if you, this L stands for liquid, that means this entire region, this shaded region, this material exists in the liquid state. Now, this is your line compound, that is Ti3B4. Line compound means it does not have any off stoichiometry range, it is essentially, it has a fixed composition. But TiB2 is not in stricter sense, it is a line compound, because TiB2 has a smaller window, of the off stoichiometric composition. So, TiB2 is essentially around 65 to 67% boron content. So, that is the range of the boron in the TiB2, and TiB2 has the melting point is 3225 degrees Celsius. So, as far as the melting point wise, TiB2 certainly can be classified as high temperature ultra high temperature ceramics, but one of the additional requirement for ultra high temperature ceramics is that these materials must be used without any property degradation at extremely high temperature. So, where zirconium diboride or niobium diboride, that actually qualifies. So, other things that are important is that it is not only the line compound or the covalent compound like TiB or Ti3B4 that is important. For example, TiB also, some of the TiB goes to, so this is the region is liquid plus TiB2. Okay. So, if you increase the temperature to above 2200 degrees Celsius at this particular composition, so TiB will melt, and this it will enter into phase domain of liquid plus TiB2 phase. Okay. So, therefore, the maximum temperature stability of all these three compounds in the TiB system, these three compounds means TiB, Ti3B4 and TiB2. The TiB2 is the best. So, I put a star here because TiB2 has a large melting point of 3225 degrees Celsius. Okay. So, other things is that that if you look at this particular phase diagram, it is this region is the liquid plus TiB. So, this would be TiB plus Ti3B4, and this is the Ti3B4 plus TiB2. Okay. So, like that one can find out that what are the phases that are present. So, you can take a horizontal line and then you can see that which are the phases that are present at two ends of the horizontal line, and that will be used as a guideline to say that what are the two phases that are stable in this particular temperature composition space. So, as I said before that we have used two different type of sinter aid. One is a molybdenum. So, that is the first set of experiments. So, in order to optimize the hot pressing conditions, we have varied the temperature from 1500 to 1800 degrees Celsius. Time is around 1 hour. So, this is the heating rate, and then hot pressing was conducted in vacuum. Now, here goes the typical data that we have obtained of the relative density, that is percentage rho Th. Rho Th stands for theoretical density. So, when you add molybdenum as a sinter aid and when you sinter them at 1700 degrees Celsius, that the black one, or 1800 degrees Celsius, what you have seen at 2.5 molybdenite content at the addition, that you are getting close to 99.5% theoretical density. So, 99.5% theoretical density is the maximum theoretical density that one can get in the hot pressed TiB2 molybdenite content at low amount of sinterate. The second thing, it is important for you to realize that while developing this wire resistant ceramics, while you need to use the sinter 8 to densify the ceramics, but one has to use the sinter 8 to as low amount as possible, so that the baseline properties of the major ceramic phase is not compromised. Let me substantiate my statement in reference to TiB2-MoSi2. So, what I am saying, for example, if you do not do these experiments, if you suddenly started using with the intuition that if you add 5% or 10%, anyway the material would be sintered to full density or more than 98% sinter density. So, if you add this 10% molybdenite, what would happen? Your base ceramic phase is lesser, right? TiB2 would be 90%. But then your baseline properties, like in terms of hardness and other strength properties, would be compromised simply because of the presence of unnecessarily higher amount of sinterate. So, one has to use simply lower amount of sinterate while achieving higher sinter density in the hot press ceramic. So, that is the major message that I wanted to send across. Now, these are the XRD traces of this TiB2 based materials. So, this is the 0% molybdenite, that is the topmost one. So, you get all the TiB2 phase, that is what you expect in the hot press ceramic. In the TiB2 molybdenite 2.5 and 5%, you see something is propping up, something is coming up, okay? And this phase is getting more and more pronounced when you add this 7.5 molybdenite. Now, if you look at the symbols very carefully, field and square, it is molybdenite, and that is certainly, that should be certainly present when the molybdenite content is 5% and more. Now, what is the other symbols? Diamond symbols, these are MO5Si3. So, diamond symbols are MO5Si3, which are also discernible, and this square circle, unfilled circle, that is this one, is Ti5Si3. So, these are the two phases that are formed presumably because of the reaction with the reaction between TiB2 and molybdenite. So, what are those reactions that can possibly take place between these things? So, one of the reaction that can take place TiB2, so essentially TiB2 and molybdenite that will react to MO5Si3 and Ti5Si3, right. So, what happens, we have to consider the two things here. Each of the TiB2 particles, it has a surface oxide layer of TiO2. Okay. Similarly, molybdenite also can have a surface oxide layer as a SiO2. So, when you use these reactions TiB2, then one has to also use this reaction, one has to also find out that what is the reaction like MoSi2 TiB2, and you can find out that how this sintering reaction product Ti5Si3 and MO5Si3, these kind of phases are formed, and there would be certainly some boron oxide or silica, that would be the third phase that is forming. Now, this is the transmission electron microscopy images for one of the composition, that is with the high molybdenite content is TiB2-MoSi2, and then each of these grains are also marked on these TM images, whether it is TiB2 or molybdenite and MO5Si3, and then corresponding selected area diffraction pattern has been shown here. For example, this is for MO5Si3, this is for molybdenite, and this is for Ti5, there is also Ti5Si3 phases these are formed, right. So, this is for Ti5Si3 and this is for TiB2. So, TiB2 is a hexagonal structure and all other silicides are also, their zone axes are also marked. So, this is the bright field images, these top panels, these images are bright field images, and you can clearly see this is the TiB2 grains and these are the larger coarse or molybdenite grains are there. So, if you look at this micron bar 0.5 micron, so certainly this molybdenite grains will have few microns like 3 to 4 microns, and TiB2 phase are fairly small. And in some of the phases which are formed the silicide phase, molysilicide and Ti5Si3, which have essentially formed at the interface between the TiB2 and molysilicide. So, we have done this wear friction and wear experiments, particularly in the fretting mode. Again TiB2 molysilicide is flat materials, and steel ball or cermet, tungsten carbide, cobalt is used as the matting material. And then these are the fretting conditions like 100 microns sliding, 4 Hz is the frequency and 100,000 cycles. The load is varied between 2 Newton, 5 Newton and 10 Newton, and frequency is 4 Hz, and there is a displacement amplitude that we have also mentioned here earlier. Now, this is the frictional properties of the TiB2 2.5% molysilicide. If you remember correctly, that this particular TiB2 2.5% molysilicide has full density and also it has higher hardness properties. So, we have selected this TiB2 molysilicide for the fretting studies, and what you see here that when the load is varied between 2 to 10 Newton. So, the difference is the friction coefficient is somewhere around 0.05. So, it is between 0.5 to 0.55. So, that there is not much difference, significant difference as far as the load variation is concerned. All right. So, this is that wear surfaces of TiB2, wound surface of TiB2 after they are fretted against tungsten carbide cobalt, that is the cermet. Interestingly, what you see here, this is a 2 Newton and this is increasing the load 2 to 10 Newton. You see there is a numerous micro cracking patterns. What you have noticed sometimes in one of the earlier lectures, that after cryogenic sliding conditions, the zirconia they experiences fish scale patterns. So, it is somewhat like fish scale patterns, very characteristic micro cracking patterns, and this micro cracks is quite interesting enough. They have formed in a group manner and this ensemble of micro cracks that are observed only at certain localized region in the wound surface. And what you notice here that around these wound wear debris wound surfaces, these wear debris particles are also present, and these wear debris particles are of different chemistry, because it is certainly from the contrast that you observe, certainly it cannot be pure titanium oxide. So, or it can be some other oxides of the TiB2 or molysilicide. At 10 Newton load, you see that more evidences against after they are slided against the hard metal. So, these are the abrasive scratches here, you can see that there are abrasive scratches, and then you can see there are small region that where there are cracking also observed. But the severity of abrasion is certainly not much, because this is what you see in the tungsten carbide cobalt ball. So, these are the wound surface region tungsten carbide cobalt, and this is the corresponding flat, that is TiB2 2.5% molysilicide. Okay. So, this is at the high load of 10 Newton, and again TiB2 10% 2.5% molysilicide, you see this cracking, this micro cracking are fairly small, and they do not coalesce together to lead to the major macro cracks. So, this is how the wound surface look like after they are fretted against tungsten carbide cobalt at 10 Newton load. Certainly you see this is the presence of the different silicide phase at TiB2 molysilicide 10% molysilicide. This can be either Ti5Si3 or moly Si3. one of these silicide phase, okay, and this is the typical wound surface area or wear region on this particular surface. Now, one of the important things in the tribology is to establish a correlation between the wear volume and dissipated energy. So, this dissipated energy one can find out, suppose you have a tangential frictional force and this is your displacement delta, and if you, most of your wear experiments, fretting wear experiments are conducted what we call is the gross slip region. So, gross slip region, if you integrate this area under the curve, that will give you the energy that is dissipated per cycle. So, if you calculate the energy dissipated per cycle and multiply by total number of cycles like 100,000 cycles and so on, for each and every cycle if you calculate separately, then it will give you the total dissipated energy. And if you plot against, it shows a very linear correlation. This is almost like the R square value would be 99.99 or something. So, all these materials like TiB2, 2.5% MoSi2, 10% MoSi2, they will follow a very linear variation of wear volume with dissipated energy. So, the question is that whether any correlation with this predictive model. So, there is another thing that we have noticed is this, in this particular case of the TiB2, it is that abrasive wear very important, and abrasive wear is a major wear mechanism. So, what we have done, like energy dissipated, another parameters we have used what we call abrasion parameter. Now, this abrasion parameter, it is not a single parameter, but it is a composite of the load, fracture toughness that we have measured using indentation cracking. So, instead of K1C, it is better to use it as a KC, because we are not using that mode 1 loading, instead we use the indentation cracking. So, if you plot that wear volume as a function of abrasion parameter, again it shows a perfect linear correlation when we plot all the data, group of the data of the TiB2, 2.5 molybdenite and 10% molybdenite materials. So, in case of both the cases, whether it is a dissipated energy or whether it is abrasion parameter, for the titanium diboride, it wear volume correlates fairly well or linearly proportional to that dissipated energy or abrasion parameter. Okay. So, having said that, next set of experiments were conducted in the titanium diboride, titanium disilicide materials. Again, we have used two counterbody materials, one is steel and one is tungsten carbide 6% cobalt. And what we have done in both the cases, that we have finished these wear experiments at different load like 2 Newton, 5 Newton and 10 Newton, and then we have done this 2D wear profile from several 2D wear profile from one end to another. One can integrate to get the wear volume. Particularly for tungsten carbide cobalt, we see that is more or less smooth 2D wear surfaces, but in case of steel there is a negligible wear. In fact, this steel tribolayer is formed on the material surface and it does not show any positive wear as far as the steel is concerned. So, if you see that from the top to bottom, the top panel is for 2 Newton load, middle one for 5 Newton load and bottom one for 10 Newton load. So, the leftmost surfaces are mostly these surfaces on the flat, that is titanium diboride. Middle column is for the steel ball, and you can see steel ball is completely covered with the tribolayer, and this is iron oxide rich layer. And if you look at the little bit close up view of this material, of these own surfaces, you will see that steel layer is not only there on the material, on the ball material, but also on the flat material. Essentially, it gives rise to 3 body wear situation. Okay. So, after tungsten carbide cobalt, so this is after against versus tungsten carbide cobalt. So, you have this 2 Newton load and 10 Newton load, and you will see in the 2 Newton load there is some occasional presence of the cracking, but mostly this is the very evidence of mild wear. At 10 Newton load, the cracking observation of cracking is much more, and you can see that there are some places these cracks are generated not only perpendicular, but also at other different angles to the fretting directions. So, now this particular slide essentially shows the wear volumes is plotted against the load, and you will see that how these wear volumes there, these field symbols are essentially wear volumes. So, if you plot against the load, so TiB2-TiSi2 case, the wear volume increases, and and wear rate actually decreases, because wear rate, when you do wear rate, it is essentially normalized with respect to load and sliding distance, and it is 10 to the power minus 6 millimeter cube per Newton meter. Against tungsten carbide cobalt, again the field circles for the wear volume, it shows some increase with load, but this increase is certainly not significant, and here the wear rate is of the order of 10 to the minus 6 millimeter cube per Newton meter. Now, when you do these tribological properties, so essentially what you see here, that although these materials they experience abrasive wear, so their wear rate is not very high, or in other words, it follows, or it is fairly similar to the earlier model ceramic materials like alumina and so on. So, they are also that wear rate varies somewhere 10 to the minus 6 millimeter cube per Newton meter. So, in the next lecture, I will describe the friction and wear properties of niobium boride, but in those cases I will be showing you the erosion wear results, but not the fretting wear results, but at high temperature. So, high temperature wear properties is somehow remains a challenge as far as the highest temperature capability of the wear tribometer. But here in this next lecture, I will show you that how the high temperature wear properties, I mean how the erosion wear varies with respect to temperature up to 800 degrees Celsius. Thank you.